Welcome to the new video of Explaino Tech. In our previous video, we mastered the components of the electric powertrain and the power flow. Now, it's time to understand the logic and flow behind the torque path of electric vehicle. We'll explain how the vehicle control unit interprets driver intent, how it negotiates with the battery via the BMS, and exactly how the inverter translates data into high voltage current, and finally the motor delivers the required torque. This is the science of EV calibration. The process starts at the accelerator pedal assembly when you press the accelerator pedal to move the vehicle. Your physical movement is converted into a precise electrical signal. Unlike an old-school cable, this is a drive-by-wire system using sensors to tell the vehicle control unit, VCU, exactly how far the pedal is pressed. The VCU acts as the car's central brain, receiving this raw data and immediately performing a plausibility check to ensure the signal is consistent and safe. Once the VCU confirms your intent, it doesn't just pass the signal through. It consults a pedal map, which is essentially a software-based lookup table which converts the accelerator pedal position to torque value. This map determines how much torque, twisting force, the motor should produce based on your current drive mode. For instance, a 50% pedal press in eco mode might request a smooth, low torque output for efficiency, while the same 50% in sport mode tells the map to request a much more aggressive surge of power. Before any power actually moves, a critical digital handshake occurs between the VCU and the battery management system, BMS. The VCU sends a request to check the battery's readiness, and the BMS responds with a status signal. This signal tells the VCU if the battery is within the correct temperature range and has enough state of charge, satiety, to handle the discharge. If the battery is too cold or nearly empty, the BMS informs the VCU to clip or limit the torque request to protect the cells. Once this safety check is cleared, the VCU packages the final torque command into a digital data packet and sends it across the car's CAN bus network to the inverter. Now that the inverter has received the digital torque command from the VCU, it must act as a high-speed translator to turn stored energy into physical motion. This process starts with the inverter pulling electrical energy in the form of high-voltage DC, direct current, from the battery pack. Inside the inverter, a bank of high-power switches, usually IGBTs or silicon carbide MOSFETs, performs pulse width modulation. By switching on and off thousands of times per second, the inverter shapes that flat DC into three-phase AC, alternating current. The inverter specifically adjusts the current amplitude, the strength, of the wave, to match the torque request. A higher demand from your foot means the inverter allows more amps to flow into the motor. This three-phase AC power is then transferred through heavy-duty orange cables directly into the electric motor, traction motor. As the AC electricity flows through the motor's copper windings, it creates a rapidly rotating magnetic field. This is the exact point where electrical energy is converted into mechanical energy. The magnetic field pulls the internal rotor around, creating a powerful twisting force known as torque. Because electric motors can produce maximum torque starting at 0 RPM, the response is much faster than a traditional engine. However, the motor usually spins much faster than the wheels actually need to turn, so this high-speed mechanical rotation must be managed before it hits the road. The final stage of the journey takes place in the transmission, which in most EVs is a simple, fixed-ratio reduction gear. As the mechanical torque enters the transmission, the gears reduce the high RPM of the motor to a lower, more manageable speed for the wheels, while simultaneously multiplying the torque. This mechanical advantage is what gives the car its powerful acceleration. This multiplied mechanical power is then sent through the drive shafts to the wheels, creating the traction effort needed to push the vehicle forward against the pavement. In just a fraction of a second, the energy has traveled from a chemical state in the battery, through a digital state in the VCU, to an electrical state in the inverter, and finally into the mechanical force that moves you down the road. So, the next time you press the accelerator, remember that you aren't just moving a pedal. You are initiating a massive digital and electrical negotiation. In a fraction of a second, your intent has traveled from a sensor to a computer brain, checked in with the battery's health, and been transformed from silent DC electricity into a powerful, rotating magnetic field. This seamless transition from chemical to electrical, and finally to mechanical energy, is what makes the modern electric vehicle so incredibly responsive. It's not just a car, it's a high-speed conversation between software and physics. Thanks for watching Explaino Tech, and I'll see you in the next deep dive into the technology. Thanks for watching. If you like the video, please share it to your loved ones. Please like the video and subscribe the channel.